Okay, so welcome to my talk about dynamic games with noise informational asymmetries. I don't know why it's showing, so that. I don't know. Let me see if it's the internet. It's any room. Okay, I guess it's what it is. I'm sorry about that. So this is joined with Francesco Fabbri, who's a grad student at Princeton. So the motivation for this paper is to define and prove existence of an equilibrium in dynamic games that are infinite. So in games that infinite types or with infinite information or observations, payoff discontinuities can arise, which make equilibrium existence challenging. This has been highlighted by counterexamples to existence, such as those by these authors. And these examples, there's even finite actions and one-stage games. There's even counterexamples to the existence of approximate equilibria. So our paper addresses these challenges by proposing a novel approach, which is the idea that players have noisy informational asymmetries, which means that they observe the private information with noise, and they cannot perfectly observe what their opponents observed or what happened in the past. We show that when you add any amount of noise, even a little bit of noise, you can get existence in a game that otherwise would not have existence of an equilibrium. Also, having noisy observations is very natural in many economic settings. In our setting, in our model or our games, what it's going to do is it's going to make payoffs continuous in strategies. And therefore, we will obtain existence results in games where the literature had not yet established existence. Oh, that was the problem, I guess. Let me see. Okay. Okay, much better. Thank you. I had a very little window. That's why I was showing like that. Okay, so our paper contributes to the study of infinite games with asymmetric information by defining a Trembling-Hanford equilibrium and proving that it exists. We also define a Markov environment for games with asymmetric information and show existence of a Markov-perfect equilibrium. Our approach relies on the introduction of an assumption which we call the sequential absolute continuity assumption, which together with other conditions yields existence. This assumption, the SAC assumption as we call it, is a generalization of Milgram and Weber's absolute continuity condition from the static game to the dynamic game. And finally, we'll link this SAC condition to the presence of idiosyncratic noise in the player's private information. Okay, so let me explain our formal setting. There's going to be a game that is played in discrete periods. So these periods are indexed by the natural numbers. It is defined by a tuple that has several elements. N is the set of players. Omega is the set of states. Xi is the set of actions of player I. Si is the set of signals of player I. Gi is a flow payoff function. And mu is a transition probability. And gamma is a function that gives you from states what the signals that the players observe. Omega and Si have to be measure spaces. Xi is the action set, has to be countable and a compact metric space. Gi, as I said, is the flow payoff, takes histories into reals, representing the payoffs of the player, I in this case. And it has to be measurable and bounded. Mu is a state transition probability that tells us how likely is it to draw a given state given the history of the game so far. And gamma is a signal transition function that gives me what are the signals of all the players, the signal profile that the players observe, given the history of the game. And it has to be measurable. In the full paper, we have a more general framework that allows having, I don't know, actions that are available that vary depending on the history or players who are uncertain about whether their opponents have played or not. But in this particular, in the presentation, I'll look at the simpler case. A strategy for a player is going to be a function that tells us what the players will do. So it's a function from private histories to probability distributions over players' actions. We are going to make two technical assumptions. The first one is the boundedness assumption. This assumption requires that the sum of the maximum possible payoff the players can get in each period has to be finite. This accommodates discounting, but it's more general than discounting. And we have a continuity assumption that says that the expected payoff at any time, given past signals and actions, is a continuous function of action history. Okay, so in order to introduce the SAC condition, I have to first define a norm that we use in the paper, which we call the strong total variation norm. Okay, so to define this norm, let's consider a measure over a set Y, some measure space, and Z is a countable set. So for each Z, this is a measure. And suppose that pi Y is the set of partitions, finite partitions of Y, okay? And suppose that we take a finite partition, an element of pi Y, indexed by a finite set, and then we take for each element of the partition an element of Z. So a collection of elements of Z indexed by this set I, okay? And then we compute the sum over the index set of these measures, the absolute values of these measures, okay? Now we've done this operation. In order to define the strong total variation norm, we have to take the supremum over all these operations. So what does this mean? We're looking at the supremum over all possible partitions and all possible collections of elements in Z, one for each element of the partition, of the sum of these absolute values, okay? The supremum over all possible partitions and collections. So we'll say that Xi is bounded in the strong total variation norm if this quantity here is finite. And we'll say that it is continuous in the strong total variation norm if for each Z star, when we take the difference of the strong total variation norm of psi restricted to be in a delta neighborhood around Z star, and Xi at Z star converges to 0 as delta goes to 0. Okay, so as Z get closer to each other, to Z star, then the difference of the measures goes to 0. Notice that in order to define continuity in the total variation norm, we would have to calculate these quantities. So it's Xi of Z minus Xi of Z star, and it needs to be satisfied that this quantity goes to 0 as Z goes to Z star. So in our notation, we can also define continuity in the total variation norm, and this notation already shows that it is weaker than the continuity in the strong total variation norm. And in fact, we have an example in the paper that shows that it's strictly weaker. So the purpose of this norm is that when you have a density, when this measure has a density with respect to a measure that is independent of Z, this density is going to have good properties if this measure is bounded and continuous in this norm. So that's in the paper. And it's useful for our results.
Sorry,
Yes?
you said that Z is countable.
Yes.
So can you clarify what is the neighborhood that you were?
So there's a neighborhood, it's countable. So a countable set, it has a matrix. So a neighborhood would be, yes?
The discrete one. The discrete matrix.
No, the discrete metric would not be compact.
So I don't, what kind of neighborhood?
There's a metric. You can have a metric on a countable set, and then, for example, if your countable set is a sequence converges to 0, then yeah, but it has to be that in that metric the space is compact. So the discrete metric on a countable set that's not finite doesn't work. Okay. So the sequential absolute continuity condition, thanks for your question, is going to be the following. So first, let me introduce some notation. This is the joint distribution over signal histories given the realization of an action history. And this is the marginal over I signals generated by this joint distribution. The SAC assumption requires two conditions. First, it requires that for every t and action history in xt minus 1, this joint measure is absolutely continuous with respect to the product measure of the player's marginals. Okay, that's number one. And number two, it requires that this joint distribution be bounded and continuous in the strong total variation norm. So the norm that I just defined in the previous slide. So notice that the absolute continuity condition in Milgram and Weber will not have dependence on previous actions because it's a static game, so no actions have taken place, and therefore this condition reduces to A in the static game. And it's exactly Milgram-Weber's absolute continuity condition. From here, we can see that SAC-A will be satisfied whenever there's countable signals, and SAC-B will be satisfied whenever there's finite actions. So in particular, our results show, as I'll say when I show you my theorem, that any set with countable signals and finite actions will immediately have an equilibrium. Okay, so let me tell you our theorems. First, I'm going to define Trembling-Hunt perfect equilibrium as a limit of constrained equilibria. So first, let me define an epsilon tremble. An epsilon tremble is a small perturbation of strategies. So it's a function that goes from private histories and actions to 0, 1. And it has to satisfy two conditions. First, the sum of the perturbations over actions has to be small, so less than epsilon. And it also has to be continuous in actions for every realization of signals. An epsilon constraint strategy has to respect these trembles. This means that each player has to assign at least the probability required by the tremble to each action. So as in the classical case, this will ensure that every action has positive probability. And an epsilon constraint equilibrium will be such that the players are best responding, constrained to take epsilon constraint strategies. And finally, a Trembling-Hunt perfect equilibrium will be the limit of epsilon constraint strategies when the trembles go to 0. So very standard. The only difference relative to the classical case is that the trembles have to be nicer. The trembles need to be continuous in actions so that our theorems work. The way we define this convergence is not totally straightforward, but you can check the paper to see the details. Now, let me tell you our main theorem. The first part says that no matter what tremble profile we take, for that tremble, there is a constrained equilibrium. And the second part says that a Trembling-Hunt perfect equilibrium exists. So because we have constrained equilibria, we can find limits of some sequences of these constrained equilibria, and those limits will be a Trembling-Hunt perfect equilibrium. And this Trembling-Hunt perfect equilibrium will also be subgame perfect. Okay, so I'll tell you our main theorem. Now let me tell you an important application of our theorem. For that, I'm going to introduce the concept of the composable noisy signals. We say that the game has the composable noisy signals. Each player's signal can be decomposed into a fundamental signal component and a noisy random variable. And then we can obtain the signal by adding the fundamental component plus the noise. The following assumption will provide conditions that guarantee that SAC is satisfied in a game with the composable noisy signals. So the condition says that the distribution of the fundamental component and the noise of the joint distribution given and past actions has to be absolutely continuous with respect to the distribution over the fundamental signal and the Lebesgue measure over the noise. Because this is absolute continuity, then there's some density here, and we require the density to be continuous, at least, but it could be almost perfect, almost surely in epsilon. Okay, and the other conditions say that whenever I have a signal, the event of there is some, which are the fundamental signals that yield that signal has positive measure. So it's not possible to infer what is the fundamental signal from the signal you observe. And finally, the third requires that the distribution of the fundamental signal is continuous in the weak convergence of probability measures. Under these conditions, the game will satisfy the sequential absolute continuity condition, and therefore this will imply existence of a Trembling-Hunt perfect equilibrium. Okay? So games with noisy signals can represent various economic situations. For example, they could represent a dynamic oligopolistic model where firms are interacting in the market, the actions are their quantities or their prices they set, and they receive idiosyncratic signals of demand. It could be that it is a sequential auction with interdependent values where the actions are the bids that are submitted in each round, and the signals are the buyers informative about the interdependent values of the values. Or a third application would be a global game of regime change in which the players decide whether to attack or not the regime, and they receive signals about the regime, and then the regime evolves according to the history of attacks. And there's other Morris and Shin, currency attacks, beauty contests, all of these have the feature where players have private signals that have a noise, usually uniform or normal noise that is added to the kind of the fundamental signal. Our results are more general than that. They called for measurable functions that are not necessarily additive. They don't have to be real vectors. And then if similar conditions hold, then we obtain SAC as well. Okay, and I'll give you I have 1 minute. Okay, very brief overview of our results for Markov games. We define a Markov game as having two types of states and signals, pair of relevant states and pair of relevant signals. Pair of relevant states determine new pair of relevant states where the pair of relevant states do not. And we assume that there's a Markov information, which means that the distribution over the pair of relevant state can be predicted using your latest signal. You don't need your previous signals, just the last one. And a Markov payoff assumption that says that the player's payoffs depend only on the current pair of relevant signal. And then instead of SAC, we ask for a Markov absolute continuity assumption that requires also an absolute continuity condition that holds not just across players, but also across periods. And for those cases where Markov strategies are those that put only condition on current pair of relevant signals, we can show that there is a stationary Markov perfect equilibrium if MAC, this modification of SAC, holds. Okay. And then in the paper, we also have several applications for which we can find stationary Markov perfect equilibria, such as oligolistic competition or games with the stochastic moves and such. Okay. I think I have a conclusion slide, but I think I'm out of time. Or can I continue? Okay. So in summary, we studied infinite horizon games with asymmetric information. We introduced the sequential absolute continuity condition, which is a generalization of Milborn and Weber's absolute continuity condition from the static to the dynamic setting. Under sequential absolute continuity, we established existence of a Drumlingham perfect equilibrium, which is also subgame perfect. We linked SAC to noisy signals, showing that SAC holds when signals contain some idiosyncratic noise. For Markov games, we changed SAC, modified it to MAC, the Markov absolute continuity condition, and under that condition, we obtain existence of stationary Markov perfect equilibrium. And this way, our results provide existence guarantees for a broader class of games for which we knew existence held.